So what we're going to do now is we're going to talk about the Java ConditionObject. And Java ConditionObjects are an implementation of the concept of condition variables. So the first part of this lesson is going to talk about what a condition variable is and what pattern is typically used, they are typically used to implement. And condition variables are tricky. Of all the synchronization mechanisms we've talked about so far, semaphores, reentrant locks, and so on, condition variables are by far the most tricky. So you might want to watch this lesson more than once and look at some of the links to really understand it. The grad students will also get a chance to play around with this for assignment 2B, so it's important to understand that as well. So let's start by giving an overview of condition variables. So a condition variable is a synchronizer that allows a thread to suspend itself, possibly repeatedly, and suspend its execution until a condition it's waiting upon becomes true. So you can think of this as sort of this endless cycle of waiting and checking and waiting and checking and waiting and checking until things finally get to where you want them to be. A thread whose execution is suspended on a condition variable is said to be blocked, so they can't make any forward progress. So you'll see how that plays out here as well. Condition variables under the hood are implemented as a queue of threads, which are typically called the wait set, that wait for a certain condition to become true. So we're going to have a queue of threads that are going to be used to wait on a condition variable. And as we'll see here, there's some properties that allow them to wait while their condition that they're waiting on is not true or not satisfied. We typically use condition variables when mutual exclusion is insufficient to ensure coordination. So the key thing here is that mutual exclusion is very good for being able to keep others at bay while we do our thing, right? We've been talking about lots of examples where you want to be in a critical section, you want to keep other things at bay while you do your stuff. That's what mutual exclusion is good for. But there's certain types of scenarios where mutual exclusion doesn't help you at all, either because it's the wrong abstraction entirely or because it's incredibly inefficient to do it with mutual exclusion. So if mutual exclusion is not sufficient, and it's typically not sufficient to coordinate things, it's good for being able to serialize actions but not coordinate things. So the issue here is, what do you do when a thread encounters some shared state that prevents it from being able to do any work at the moment? So here's a simple example. If you have a thread that wants to put something in a queue, but the queue is full because it's very long, that's an example where the thread can't make forward progress. It can't do its work because the shared state isn't in the right state. In other words, the queue is full. Conversely, or equivalently, if you have a situation where you want to remove something from a queue, but the state of the queue says the queue is empty, then once again, if you use mutual exclusion for that, you'll sit there and spin and spin and spin, which is not what you want. You want to be able to do something else. You want to be able to put yourself to sleep or suspend yourself until that shared state gets to a point where you can do something useful. Yeah?
What is the overhead of sleeping?
What is the overhead of sleeping? Great question. So the overhead of sleeping is on the order of thousands of instructions to do a preemption, the thread preemption, suspend an existing thread, the thread that's trying to go to sleep, wake another thread up, let it have a chance to run. So it's on the order of thousands of instructions. Those thousands of instructions go by pretty fast these days on a modern processor, but there is overhead to it. So you typically don't want to sleep unless you have to. But I guess another way of asking the question is, what's the overhead of not sleeping, right? So, and the answer is it depends, right? So if you're in a situation where something will only be locked for a very short period of time, and there's low contention, there's lots of other things trying to get it, you might be better off spinning for a little bit. If it's going to take you less time, less instructions, or less time, or less resources to spin a couple of times and then acquire the resource, you're better off spinning than you are putting something to sleep. So, but it all depends, right? So there's no one right answer. If you're building a nuclear reactor temperature control, monitor, you probably want to spin because you've got to know that temperature, and when it starts to overheat, you want to shut it down right away. So sleeping might be too much overhead. In other situations, you might want to sleep. What makes this particularly interesting is that nowadays, with multi-core processors, it often makes more sense to try to spin for a while, because putting a processor to sleep nowadays is very expensive because of all the caching that's taking place. So it depends. But we're in a model where we're going to be in a scenario where we want to sleep, right? So we can't make any useful progress. And a good example would be the fair semaphore we were just talking about, right? You don't want to have all those threads sitting there spinning. That would be crazy, because they'd wear out all the cores, and they would actually get nothing useful done in the system at all. So let's talk about this pattern that, oh, yes?
So will wait have more overhead than sleep?
Well, OK, good question. Does wait have more overhead than sleep? Wait and sleep are used for totally different things. Sleep just says, I'm going to take a nap. Whatever the heck's going on, I'm taking a nap for 500 milliseconds. Wake me up when my nap is over. If anything happens between, if anything becomes available, I'm just taking that nap. I'm going to put my headphones on, my eye patches on. I'm going to turn the noisemaker on. I'm just going to sleep. Wait is different, because wait is going to be waiting until the condition changes, so that might happen very rapidly. So wait and sleep, even though you can do timed waits, they're being used for different things, because sleep is just put me to sleep, wake me up when I'm done with my nap. Wait says, park me over here for a time until the resources change. And keep in mind that that might be very quick, or it might be very long. So with sleep, you'll wake up after the allotted time, but whatever resource you're looking for still may not be there. So sleep, in general, sleep is not a good thing to use. Wait is a much more useful thing to use. Let's talk about the pattern that condition variables typically implement. This is something that's called the guarded suspension pattern. I was trying to come up with some visual metaphor to think about guarded suspension. So I decided Gandalf on the suspended on the bridge was my metaphor. Not really very good metaphor, actually, but it was the best I could do. So if you take a look at the guarded suspension pattern, you'll see that this is a pattern that's used when an operation, in order for an operation to run, two things have to happen. A lock has to be acquired, and a precondition has to be satisfied. So this is guarded suspension. What that's saying is, basically, put me to sleep until this condition is satisfied. That's what guarded suspension is all about. And you'll see that guarded suspension is really the most canonical way in which condition variables are used. All right. So let's take a look at an example. Thread 1 here is going to suspend its execution on a condition variable until some other thread notifies it that the shared state it's waiting on may now be true, or may now be satisfied. Whatever it is that it's waiting on, the predicate, the state, the condition, whatever you want to call it, might be satisfied. And it's going to wait until that happens. And notice the tentative nature of may, right? Because just because it's going to be awakened doesn't mean that the state actually is true. It means it may be true. So we get a chance to check. So this is going to work, and this is kind of the canonical use case. First, a lock is acquired. So we're going to grab a lock. And we'll talk a bit more about where that lock comes from in a minute. So the lock is acquired. And then while the condition is not satisfied, so notice the loop here. This is sort of the canonical case. While the condition is not satisfied, then we're going to wait. But when the condition is satisfied, then we're going to go ahead and do our thing with the lock held. This is the crucial thing to remember. The lock has to be held while this operation runs. However, if the condition is not satisfied, we're going to wait until it might be satisfied. And when we call wait, that's going to go ahead and release the lock. So when wait is called, the lock will automatically be released. So the lock will be unlocked. So now let's assume, for sake of argument, thread T1 is here waiting, blocked. Thread Tn, some other thread, comes along, and it's going to signal the condition. And that's an indication that that first thread, the waiter, might have its state satisfied. Yes, Ankur?
Wait differ from just wait.
How does await differ from wait? Oh, great question. So the question is, how does wait, remember we've been talking about wait in the context of the Java built-in monitor object, and now all of a sudden we've got await. And the next question you're probably going to ask me is, how does signal differ from notify, right? So built-in monitor objects have three operations: wait, notify, and notify all. condition variables typically have await, signal, and signal all. They do more or less the same things. They're just working on different abstractions. And you'll see how that works out. I think that they chose those names to avoid totally confusing people by using exactly the same names that you had for the built-in monitor objects. OK, so when another thread signals the first thread through the condition variable, that's an indication that the state may now be in the right position. And if that's the case, the lock is reacquired, and the condition is rechecked in the loop. So we check again, we loop back around, check the condition with the lock held. And if it's OK, then we go ahead and do the processing. These conditions, which are sometimes called predicates or condition expressions, can be arbitrarily complex. I show a method call here on the slide, but in fact, oftentimes they're just an expression, good old expression that you'd have in a loop, that involves shared state, variables, objects, whatever. So you can have whatever you need to do to check the condition. And that can be arbitrarily complex. Because it can be arbitrarily complex and because it can be shared, then it needs to be protected by a lock. And the lock has to be locked while the condition is being checked, as well as when we do the processing. As we talked about before, when you wait or await on a condition variable, that atomically releases the lock and suspends the thread. So we call unlock, and that will go ahead and unlock the lock. And then the thread is suspended, so notice it was running. The lock is unlocked. The thread is suspended. It's sleeping at that point. Another term you sometimes use here, you hear used here, is parked. So the thread is parked on the condition at that point. The thread is suspended until somebody signals it, as we saw before. Notice that you need to have acquired the lock before you signal. And when the thread is signaled, it'll wake up, and then it'll go ahead and reacquire its associated lock, this thing. And after the lock is reacquired, then we typically check the condition, with the one exception of the specific notification pattern we used for the fair semaphore. But in normal cases, you would go ahead and have the lock held and put this in a loop. After the lock is reacquired and the condition becomes true, then the operation can proceed with the lock held. And if it doesn't get it, then it has to go back to waiting again, which releases the lock. So those are sort of the canonical steps that are involved. So that's the end of the overview of condition variables. You'll notice that I referenced a few sort of Java-ish-like things, like I used the names await and signal all, but I was really talking more generally about the concept of condition variable. So continuing along with our Java ConditionObject lesson, we're now going to talk about how you could apply condition variables in practice. And we'll talk about a human-known use of condition variables, which is one of my favorite examples. So let's talk about how people apply condition variables. And I'm doing this before I talk about the mechanisms of using condition variables, because I think it helps to see the bigger picture. So condition variables are very powerful, but they can be hard to grok or understand and apply correctly, because there's a number of things that make them tricky. One thing that makes them tricky is that the protocol for using them involves several moving parts. If you want to amuse yourself, do a Google search for moving parts images, and you'll see all kinds of really funny images of people getting their hand crushed by moving parts and stuff like that. I decided to go with the more sedate version here, but the good point is be alert. They're moving parts. In particular, there's a monitor condition and a monitor lock. So there's more than one thing, and that's what gets them a little bit complicated to use. The other thing that makes them hard to use is the non-determinism of concurrency, where things occur in different ways, in different contexts, based on non-deterministic scheduling. And so as a consequence, you might need to use a loop to recheck to see if the condition is actually satisfied. Just knowing that you've been signaled is not enough to know whether or not you can make progress. And those two things typically throw people for a loop, no pun intended. And this diagram up here, which comes from a book I wrote, shows the canonical steps involved in using conditions and monitor objects to implement, or monitor locks to implement a monitor object. And I won't go through all this stuff right now, but just looking at that, at face value, it's like, wow, there's a lot of moving parts, right? That's the thing that should come to your mind. Now, it turns out, mercifully, that once you understand the pattern, it's just the same thing over and over again, number one, and you'll see something else that's merciful. So because condition variables are tricky, and they're moving parts, and there's non-determinism, blah, 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 very few applications use them directly. They're almost always hidden within other abstractions. So, for example, lots of the higher level synchronizers that are available in Java use condition objects, and they hide them from you. So condition variables or condition objects are used in blocking queues and decks in the Java util concurrent package. We'll see some examples of that, such as the array blocking queue, which we looked at a little bit earlier, but we're going to talk about in more detail when we get later. Probably not today, but next time. Java built-in monitor objects, which we've been talking about, and you'll learn more about that when we talk about those lessons. And of course, the monitor object pattern, which you can read about here, which is heavily based on the concept of monitor conditions and guarded suspension, right? So all these things typically get used together. But you very rarely see this stuff in your apps. You see them in libraries that hide the details from you. Doesn't mean you shouldn't know how they work. It just says that once you know how they work, your first order of business should be to hide them so that other people don't have to know how they work. Let's talk briefly about a human-known use of condition variables. I can't remember if I've told you this one before. It's a great example. I think I might have talked about it briefly, but now I'll show you a visualization. So the pizza delivery protocol, where you need to be able to have a couple of things in order to do your job. You need to have a pizza, and you need to have keys, and that'll allow you to take the pizza and deliver it in the pizza truck. By the way, if you have a pizza truck, you get a lot of pizza to deliver, right? I've never seen a pizza truck before. But when I was looking for stuff online that was a free image, that was the best I could do. I mean, think about how many pizzas go into a pizza truck to make it economical. Most of the time, you have like a pizza compact car or a pizza bicycle or something like that, right? So the idea here, as you may recall, is that you want to get some extra work, and so you go to work in a pizza joint with some of your friends, and because this is a second job, you're going to sleep when you're not actually doing work. And the way the protocol works is the people call their orders in, the chef or chefs make the pizzas, and whenever a new pizza is done, they put it out on the counter and they ring a bell. And then everybody who's sleeping wakes up and they all try to grab the pizza, right? And in order to be able to deliver a pizza in a delivery truck, you need to have a pizza and you need to have the keys. So you need to wait for two things, or there are two things you have to have, two resources, pizza and keys. But those are independent resources. So when a person comes back from delivering a pizza or pizzas, they put the keys back on a hook and they ring a bell. And then everybody wakes up and they all try to grab the keys. So you have to get the keys and the pizza. And if you think about this for any length of time, you'll realize that it would be incredibly inefficient if the people who are the pizza delivery folks who didn't have a pizza to deliver or the keys spent their time obsessively racing to the counter and looking for the pizza and racing over to the hook and looking for the keys, right? That, you're already working a second job, you're tired, you want to sleep. Why would you sit there and spin manically trying to get all these resources? Well, you wouldn't. Instead, you wait until you can make progress. And there's multiple things that you have to have in order to make progress. It's also important to remember in this scenario that when people go to try to get the resources, that they acquire them in the same order. They acquire the keys followed by the pizza, or the pizza followed by the keys. If one group of people grab the pizza and one group of people grab the keys, what happens? You deadlock, right? Because you can't get them. So you always have to acquire them in the right order. Okay, so that's the scenario. That's a good example of where a condition variable or condition object will help you. All right, that's the end of that one. So now on part 3 of this lesson, what we've done at this point first is explain what a condition variable is, talk about some examples of how they're used, why they're a little tricky to use. I gave a human-known use. And what we're going to do at this point is talk about how condition objects enable concurrent programs to have multiple wait sets per user-defined object. Recall that a wait set is just a set of waiting threads. So let's talk about condition object. Now we're moving from concept into Java APIs and Java semantics. So a condition object is used to provide a condition variable abstraction in the context of Java. You can see that's a class. The class implements the condition interface, which you can read about here. It's definitely worth reading about the condition interface. It'll give you a sense of what they're trying to do here. It also talks about one of the questions I think Ankur asked earlier about wait, notify, and notify all. Why do they not have those methods? Why are they called signal or await, signal, and signal all? And it just basically says we're factoring out these things into distinct objects to allow multiple wait sets per object. And that's a really important thing to get your head around what that means. And we'll talk about that in a second. ConditionObject is actually implemented as a nested class that's tucked inside of abstract queued synchronizer. Recall that abstract queued synchronizer is this framework that is used by Java synchronizers that rely on FIFO wait queues, such as ConditionObjects, as we'll see in a second. So this funny syntax simply says this class is nested inside of this one. A ConditionObject provides a wait queue of nodes. So here's a node. There's actually a data structure nested inside of this called node. And a ConditionObject basically has a linked list of nodes that are linked through first waiter and last waiter. So it's basically a linked list with a first head pointer and a tail pointer. So to make it easy to add things at the beginning or the end, and to remove things at the beginning, or arbitrarily in there if you need to. So that's basically what the internal state looks like if you were to peek inside of abstract queued synchronizer. And this wait queue of nodes enables a set of threads, called the wait set, to coordinate the interactions by selecting the order and or the conditions under which they run. And of course, typically it's based on the condition, right? It's the condition expression or the predicate that's checked to see whether you can make progress. Condition objects are always used with a lock. Really, really important to remember this. With things like monitor objects, the built-in monitor objects that come with Java, it's kind of inherent in the way that they work because of the fact that when you call wait, you release the synchronized lock that the wait is associated with on the monitor lock. But with condition objects, you have to have a separate lock that's used. And it's typically, although not always, a reentrant lock. And this lock is used to protect shared state in the condition expression from concurrent access by multiple threads, as we've talked about before. You get the condition by calling new condition, which is a factory method on the lock that returns a condition object that implements the condition interface. So new condition actually returns to you what looks like a condition, but under the hood, of course, it's a condition object, typically. And that condition is bound to the lock, just like Sauron's will is bound to the ring, right? They're one and the same. Both reentrant lock and condition objects have internal queues. This is a little bit implementation detail, perhaps more than you need to know, but just if you're curious, there's queues in the reentrant lock that are used to queue up the threads that are waiting to acquire the lock, and there's a queue in a condition object that queues up threads that are waiting for some condition to become true. So the point is that there's queues galore. And by the way, those queues are typically implemented by the abstract queued synchronizer framework. So someone has done the job, Doug Lee, the concurrency genius who wrote this stuff, has factored all that code out. And that's why condition object lurks inside of abstract queued synchronizer framework, because it relies heavily on its internal details. A user-defined Java object, in other words, not one that's provided for you by the virtual machine, Java execution environment, can have multiple condition objects. That's the key thing to note. So here, for example, we have array blocking queue, which I don't think we'll get to today, but when we talk about it later, you'll see that it has two condition objects, not empty and not full. It's really important to understand this. Multiple condition objects enabled more sophisticated and efficient ways to coordinate the interactions of multiple threads. And I strongly recommend you read this link. I was having fun reading it last night as I was preparing for class today. And it does a really nice job of differentiating between condition objects and the benefits they provide, which I'll outline in a second, and built-in Java monitor objects, which are stunted and limited. And it shows a really nice example of how that happens. So by being able to have multiple wait sets per user object, they can share a lock and be notified on different conditions. In other words, not empty versus not full. So that is a big win. In contrast, built-in monitor objects only have one monitor condition, which is they call the wait queue. There's just a single one of them, and we'll talk about that later. And as a consequence, that lock and that queue get overly notified. They get notified all the time. And if you read, again, if you read this article that I wrote a number of years ago, and you read this article, which I just pointed out before, they'll show why you end up having to wake up producers and consumers on every change to the queue, even if you can't possibly allow a given thread to proceed. And one of the other consequences is you typically have to use notify all, which wakes everybody up for various reasons, and that just gets completely ridiculously excessive and cumbersome and inefficient and awkward and just bad. So that's why they ended up adding condition objects, because of the limitations with the way that the wait queue, single wait queue worked on a monitor object. It's not to say that monitor objects don't have their place. It's just the built-in ones don't have their place. It's just that the minute you get anything more than really simple use cases, they fall apart. So let's briefly talk about some of the key methods in condition object. There's not a whole lot of them. There's really 3. And these are implemented via the abstract queued synchronizer framework. They're very similar in their names to the built-in monitor objects, just await instead of wait, signal instead of notify, signal all instead of notify all. Await suspends the calling thread until it's signaled. Signal moves the longest waiting thread from the queue for this condition object to the queue for the lock, so that it can then be acquire the lock and do its thing. And all signal all does is just moves all the threads that are waiting onto the owning locks queue. So as it implies, it moves them all. Be very careful when you use signal all, because this can lead to what's called the thundering herd problem, which you can read about here. And the thundering herd problem occurs when you wake everybody up, but only one thing can make progress. So that's kind of like going back to the known example of the pizza delivery example we talked about, where you wake all the pizza people up, but only one person can get a pizza and the keys. And so everybody was awakened unnecessarily, and they all have to turn around and go back to sleep. But the act of waking them all up consumes a lot of resources. There are a few other methods on Java monitor condition object, and this will take very little time. So there's a bunch of await methods. This is the one you get normally, just the one that blocks. Then we have a bunch of ones that are timed. You can time based on nano timeout, nanoseconds, basically microseconds or time units, and days. So you can do dates, which is a more absolute time frame. And you can also await uninterruptedly. By default, await will be interrupted. Await uninterruptedly will not be interrupted. So you have to decide which one to use. And unlike the horrible timed wait calls that are in Java built-in monitor objects, which give you no useful information about why you returned, these timed calls will tell you, this one await and that one await, will tell you sort of what happened. And so does await nanos. So you can find out whether you timed out or not. OK, that's the end of that slide.